Speaker is Lidia, who will tell us about thermoelectric materials. So thank you very much.
Thank you. Hi, everyone. Can you hear me well? So it's a pleasure to be here and have the opportunity to share a little bit about the work that I have been doing. I want to thank the organizers for the invitation. So my name is Lidia Gomes from Universidade Federal de Pernambuco, where I started the position only a couple of weeks ago. So most of this work was actually done while I was a postdoc in the University of Illinois in Urbana-Champaign, including a period here at IFT. So today we'll talk a little bit about our computational efforts on trying to understand and control carriers in complex semiconductors. And we have been doing this using density functional theory predictions, combined with this experimental technique called phase boundary mapping, in order to understand and engineer defects to optimize properties of thermoelectric materials. So I start with a very quick overview about thermoelectrics and why we care about carrier control. So thermoelectrics are material that can convert temperature difference into electricity, so it's a great option to generate clean energy from wasted heat. So this is just an example of a typical thermoelectric device, which is built by many semiconductors doped N and P type. So our idea is to optimize the properties of each one of these semiconductors and then increase the performance of the whole device. Some of the properties that are of interest for us are the Seebeck coefficient, which is basically the proportionality constant between delta T and delta V. So we want materials with high Seebeck, so a small delta T can generate a large delta V in principle. We are also interested in materials with high electrical conductivity and low lattice thermal conductivity. So when you combine all of these properties, we define the thermoelectric figure of merit, ZT. So we are looking for materials with high ZT. And by high, I mean something in the range 0.6, 0.7 is what the range for the best thermoelectrics nowadays. So although this seems a good option to generate electricity, we are still looking for options because the current best thermoelectrics are still very low. They still have low efficiency to be cost effective, or they are expensive, or maybe including toxic elements. So we are still looking for ways to improve the properties of the already known thermoelectrics, or alternatively find new thermoelectric materials. So for decades, and it's still true, most of the applications of thermoelectric devices are in space applications. So we want to bring this to our everyday lives. So why we care about carrier control? So because basically all of these properties, they depend strongly on the carrier concentration. So if we can control carriers, in principle, we can control ZT. And to have an idea, so we can see how the Seebeck coefficient decreases with increasing carrier concentration, and how electrical and thermal conductivity increase with carrier concentration. So this is a reason why it's so difficult to obtain high ZT thermoelectrics, because all of these properties, they are interconnected. So we want to try to control one of them. We always have impact in the other one. For instance, if we try to decrease the lattice thermal conductivity, most of the time we also decrease the electrical conductivity, and then we have a negative impact on ZT. So it's very difficult to have a balance and control ZT in this sense. So if you look at ZT as a function of carriers, we usually have this behavior where we have a peak region where we expect to have maximal efficiency of our thermoelectric material. And this region is usually in a region of heavily doped semiconductors, something between 10 to the 19 to 10 to the 21 carriers per centimeters cubic. So ideally, we want to look at a material, candidate thermoelectric, and then tune the carrier concentration to reach this region. And by tune, I mean both the carrier type and concentration, because some materials, they have better thermoelectric properties if they are N type or P type. So ideally, this is what would be good. But unfortunately, it's not always possible to do this because of limits in dopability, which is specific for each group of material or different materials. But in an attempt of doing this control of free carriers in the material, we need to have a deep understanding of structural defects and control of structural defects. And both native or intrinsic defects, like vacancies in interstitials or anti-sites in the case of binaries, ternaries, or quaternary materials, and also how extrinsic dopants are efficient to also help in the control the carriers in the material. So in order to do this, we have to need a deep understanding of defects in materials in the point of view of theoretical or computational approach. What we want to do is to compute defect formation energy. So for a given material, different defects in different charge states, and for this, we usually use this expression. So all of these quantities can be computed from DFT total energies. So if we are not familiar, just to give an idea, this, for instance, would be the total energy of the system with the defect in the specific charge state. And then we compare this with the total energy of a bulk, perfect material. And we need also these two terms, which accounts for the elemental and charge reservoirs, which takes into account the different number of elements to create the defect, or charge to create the ionized defect. Okay, so once you have this for a given material that we study, we can then understand how we can assess dopabilities assess dopability in this material, to which extent we can control the carriers in this material. And how we do this, again, so if you are not familiar with this area, so if you are looking into the expression to compute the defect formation energies, if you are looking for a material of interest, what we do is just to compute for all different defects, intrinsic defects in the relevant charge states, we compute delta H. And then we usually compile these results in defect diagrams, where we have delta H as a function of the Fermi energy. So you can see that this relation is a linear relationship, and the slope of the curves is basically the charge of the ionized defect of interest. So acceptors will have negative slopes in this plot, and donors will have positive slope. So we just put all of this information, these defect diagrams, and then it can extract important and relevant information for us. One of them is the position of the equilibrium Fermi energy, which will tell us if the material is intrinsic, p-type, or n-type, for instance. And we can obtain this equilibrium Fermi energy from the charge neutrality condition. N and p are the free electrons and holes in the system. And then when we set the equilibrium Fermi energy, we can have well-defined formation energy for the different defects. And then we can compute the charge, the carrier concentration for each from different defects, and then the total carrier concentration in the material. So another important information from here is this region that I highlighted here, which we usually call a dopability window. So dopability window, it's basically a region in the band gap, and I forgot to mention, we usually do these plots from the valence band maximum to the conduction band minimum, the semiconductor. So this dopability window, it's the range that in principle we can tune the Fermi energy, for instance, by including extrinsic dopant, and then control the carrier type and concentration in the material. Ideally, you want to have large dopability windows, so we have more freedom to control the carriers if we find effective extrinsic dopants, but usually this is not what happens. So most of the materials, or many of them, we have limits in doping, so it's not always possible to control the carriers in the way that we want. So this is a toy example of a material that would be hard to dope p-type because of this small dopability window, which is introduced basically by this donor low energy defect, which limits this dopability window to this range. And then we have also an example of a material that it would be hard or impossible to dope any type because of this acceptor here. And these defects that limit this dopability window, we usually call them killing defects. So by dopable materials, I mean materials where native defects allows the control, the shift of the Fermi energy close to the desired band edge, valence band maximum or conduction band minimum for P or any type, instead of forming compensating defects. So this is what we want to understand in different groups of materials. And I just want to call your attention that, of course, in a given material, you don't have a unique defect diagram or unique dopability window. This can be controlled by the chemical potential term, which is basically control of the synthesis conditions. So we can change this by changing the synthesis condition in the material. So this is what has been done in this project, which is part of a big project where the idea is to accelerate thermoelectric materials discovery via dopability prediction. So involved a large group of PIs from different universities at USA. So we have Professor Tauber, Snyder, and Michael Tony from synthesis and characterization, and also Professor Vladan and Ella Fertic from the theoretical or computational side. So we have investigated different groups of materials to try to understand these limits in dopability. And together with Professor Erteking, I have been focused on diamond-like semiconductors. So materials with the structure of diamond, but very rich chemistry because they can be binary, ternaries, or even quaternary compounds. And later I'll talk a little bit about two of these ternary compounds. But before that, I was just to have a general idea of what is this phase boundary mapping experimental approach it's about. So if you want to know more, there is this tutorial from Professor Snyder group that was recently published, so you can have a look. So in a few words, phase boundary mapping, in a phase boundary mapping approach, different thermodynamic states of a single thermoelectric material can be explored. And this is done by purposely introducing secondary phases during the synthesis, or otherwise setting the chemical potential of a thermoelectric material. So let me just try to expand a little bit on this, using this example from this reference, where an hypothetical binary compound with AX and BY composition, and this would be the phase diagram from pure A to pure B elements, with this binary would be somewhere in the middle. And these binary compounds are usually called line compounds. But if you have a close look on this region here, we see that this is not actually a line. We always have like a small width in this region here. And this is because of thermodynamic requirements of stoichiometry. And so basically the presence of intrinsic defects in the material. So this small width, it's always there, but it's usually very small, but it defines these two boundaries. And in these two boundaries, we have actually the definition of two distinct thermodynamic states. So we have different values of chemical potentials in each one of these regions. And usually if you grow our material in one thermodynamic or another thermodynamic states, in some cases we can have completely different properties in the material. So because of this width, it's usually very small. It's very common, it has been observed that it's common if you just have a small change in the composition when you are growing your material, you can jump from one thermodynamic state to the other and then control the properties in a very effective way. So this is just some examples of applications of phase boundary mapping. One is on manganese antimonide, which is a zintal compound. They are predicted to have large or high thermoelectric performance if they are doped any type. But most of the zintal compounds, including this one, are known to be mostly P-type materials with very difficult, for a long time they try to achieve any type conductivity in this material. With both control of intrinsic and extrinsic dopants, and they were not successful. And recently, they were able to obtain any type conductivity in this material, but without a real understanding or deep understanding of why. And with phase boundary mapping technique, Professor Snyder and Ono, and this is the first paper where the name phase boundary mapping appeared. And they were able to explain why or how you can obtain any type conductivity in this material. So basically, the persistent P-type conductivity is due to manganese vacants, which are very common in this material. And combining DFT and this approach, they were able to assess this second thermodynamic state, which is manganese-rich region, and then increase the formation energy of these defects, and then with some extrinsic dopants, achieve any type conductivity in this material. And you can see also how we can change the Seebeck coefficient when we explore these different thermodynamic environments. Another example is bismuth telluride, where once again they could obtain both P-type and any type conductivity in this material. And you can see here that this was possible, just change a very tiny fraction of tellurium in the material. So they could jump or explore or access these different thermodynamic states, and once again change the type of carrier concentration in this material. And again, the Seebeck coefficient also changed a lot. And I'm showing here the Seebeck coefficient, but this has been shown to be very efficient to change all the relevant properties for thermoelectrics, like electrical conductivity and also lattice thermoconductivity, basically because we are changing the concentration type of defects in the material when we assess these different thermodynamic environments. So, of course, this can be extended to ternary and quaternary compounds, more complex semiconductors. So this is an example of a ternary compound. And the compositional space, again, for this hypothetical ternary compound, we don't have a point in the compositional space. If you zoom in, we see once again that we have a width in this region here because of intrinsic defects. And also, in this case, we would have at least 3 different thermodynamic states that could be explored. Reality is a bit more complex. We have the presence of secondary phases or other materials competing materials that can be there. So in this example, we'd have at least 1, 2, 3, 4, 5, 6, 7 different thermodynamic states that could be assessed. So explore all of these different states experimentally is very time consuming, and so it's very difficult, even and more in terms of reproducibility. So that's why DFT predictions are very important to be combined with this technique. So using DFT predictions of phase stability diagrams can help a lot if you do this job well in predict these different thermodynamic states and how we could assess any of them, and also predict the defect properties in these different environments. And I'll try to show next how we do this using DFT in combination with phase boundary mapping. And for this, I will use the example of a ternary material that we have been looking at, silver indium ditelluride. In the compositional space, we would have a point like here, 25% of silver and indium, 50% of tellurium. And when we consider secondary phase or competing phase, we create these regions, which are regions of 3-phase equilibrium regions in the compositional space. So for instance, this 81 region would be a region in equilibrium between silver indium ditelluride, bulk tellurium, and silver telluride. And you can look at the same way for the other regions. So basically, all the samples that are growth in this region here, they would have the same chemical potential values. And then we can combine this connection between theory and experiment is basically done because we can directly connect chemical potential and compositional space. So for instance, how can we build this chemical potential space for this compound? We can start with the planes of rich silver, indium, and tellurium, which are basically planes that form this type of cube. And then you can start introducing secondary planes of where other elements or other materials are more stable. And then we just start making cuts in this cube where other materials are more stable, just following this formation and enthalpy expression. And then we can identify here in the chemical potential space the region of stability of our material of interest. Silver indium ditelluride is then stable in this region here. And then we can identify the boundaries of stability of this material. And then we can connect direct with the compositional space. For instance, if you look at this 81 point here, which is, again, a 3-phase equilibrium point, or sometimes it's also called invariant point, we can see that it's a region where the plane of 3 compounds, they meet each other, silver indium ditelluride, tellurium, and silver telluride, which is basically this region that I just mentioned to you. So basically points in chemical potential space, okay, thanks, can be connected to areas in the compositional space. Okay, so we have been looking at these diamond-like semiconductors in collaboration with Jess and Vanessa from Colorado School of Mines, and I will just give a very general idea why you are interested in these materials. So basically, recently, Jan and collaborators have done a high-throughput search for thermoelectric candidates, and they have identified these DLS as good candidates. Here we have the predicted mobility as a function of the inverse of lattice thermoconductivity. So good candidates are in this region. And you can see that the size of these circles basically represent the thermoelectric performance. So we can see that these DLS compounds, they are predicted to have good performance if they are doped N-type. P-type compounds, they have much lower, are predicted to have much lower efficiency. The problem is that most of these DLS are known to be intrinsically P-type, and what we want to answer here is there opportunity? Can we make these materials N-type or not? So I think I have time just to talk about this one, so let me go quickly here. So we have worked with Jess, which looking and growth some samples so we could compare with our predictions. So first, to do this job right, we have to have a good prediction of phase stability diagrams, and this we have done and compare with the experimental compositional diagram, and we see that we can really identify and use DFT calculations the boundaries of stability here, and then the different thermodynamic states. And then with this, we could compute for each one of these boundaries of sets of chemical potential values. We can then compute the defect diagrams and see how it changes these dopability windows. So the dopability windows here, you can see that they change a lot if you change the growth conditions or the chemical potentials. But basically for this material, copper-indium ditelluride, there are 3 defects that sets the dopability. So copper vacancy and copper indium copper antisites. So basically a balance between these 3 defects will define this dopability window. So we can see here also why this strong behavior or P-type behavior is observed in this material. So basically, copper vacancies are well known to be observed in this material, and most of the times it's attributed to the P-type conductivity is attributed to the copper vacancies. So we can intuitively just think, okay, let's go just to a copper-rich condition and get rid of this copper vacancy and then dope this material P-type, N-type. But when you do this, for instance, in this 0.8, we can see that these acceptors start to have very low energies. So that's why this persistent P-type behavior happens in these compounds, because if you are in copper-poor or copper-rich condition, there will always be acceptor that will dominate. But we could identify at least 2 regions where a balance between these 3 defects actually defines a relatively large dopability window. And we see some hope to find some extrinsic dopant that can make this material P-type. So here I'm just going to show, I think I'm running already out of time. Okay. So I will just show some attempts of growing the samples and compare with our predictions. So just grow these 3 samples here in one of those regions that has a relatively large dopability window, and we can see that our theoretically predicted carrier concentration as a function of temperature agrees well with the experimental measurements. And we just went to the opposite region, a copper poor environment, and once again, we see a very good correspondence between theoretically predicted and measured carrier concentration. And with this, that we see that we can actually identify the low energy defects in these samples using our DFT predictions. So what we are trying to do now, and Jess has been trying to do this for a while, is to find a proper extrinsic dopant to find N-type conductivity. We are not there yet, but we hope to get there. So I'm just running out of time. We did something similar for silver indium ditelluride with Vanessa. And once again, these are basically the same results, but presented in these called Brouwer diagrams, where you can see how the carrier concentration changed when we run around the boundaries of the chemical potential here, and once again we found for this material as well some regions where we see some hope to find any type conductivity here. So in summary, I just show the importance of carrier control in trying to optimize thermoelectric properties and how we can do this with DFT predictions of these using defect diagrams, a very brief overview of phase boundary mapping where we use secondary phases to define the chemical potential and then control the defects in the material, and also how can we do this correspondence between DFT and this experimental approach. And I also show how we can make a good prediction of ideal synthesis condition to try to achieve any type conductivity in these thermoelectric candidates. So I just want to thank the team that worked mostly in this work, the founding agency, and finish with this quote from Professor Collin that I really like, saying that crystals are like people, it's the defect in them which tend to make them interesting. And thank you for your attention.
Okay, we have time for questions.
Thank you for a very interesting talk. I have a basic question regarding this phase boundary mapping that you showed. Mm-hmm. Do I understand correctly that this is a first order phase transition and you have a coexistence region between two phases? So in this sense, those lines are actually the spinodal lines between the two phases. Is this a correct reading of this situation?
This defect, sorry, say it again, the final part?
Because then you have a first order phase transition between two phases. You usually have a coexistence because you have hysteresis and so on. And so you have a region where one phase is metastable, the other one is thermodynamically stable. And this metastability can be very long in time, and you can prepare the sample in that metastable state, and it will live forever, basically, in that state. Is that what's going on here?
Yeah, exactly. You can actually, so I didn't mean that I jump like in the same synthesis condition, but we can define and grow the same nominal composition either here or here. So each one of these states are stable states,
right?
But we just define them by making them slightly slightly secondary phase, and then which is so our material is in equilibrium with the secondary phase, exactly.
So, but in the gray region, am I correct to understand that you have in your sample, because of coexistence, thermodynamic coexistence of two phases, one metastable and the other stable, that you have an inhomogeneous state where you have bubbles of one phase coexisting with bubbles of the other phase? Maybe I'm wrong. I'm just want to understand the physics.
If I understood correctly, actually this region, it's very small because there is no secondary phase. It's just one pure phase of the material of interest. The only difference here is that we have defects here. But this region is so small that we can't actually experimentally access this region here.
Okay.
Because it's really small. It's just there because of the presence of the presence of intrinsic defects. Usually are either here or here.
Okay. Maybe we're saying the same thing with different words. Maybe we can discuss later. Thank you.
Yeah, maybe. Thank you.
Very, very nice, Lidia. So it's nice that you are interacting with experimentalists for them to try to grow these materials under the conditions that you are suggesting. But a major problem is that you tell them, oh, chemical potential must be 1 electron volt or minus 1 electron volt, and they have to transform this to some experimental setup. So how do you translate from electron volt to, I don't know, concentration of, so how does this happen?
Yeah, what we tell them, it's not the numerical value, let's say, of the chemical potential. What we say is that, okay, if you grow this compound in equilibrium with this and this phase, you are in the region that we want. It's not really the numerical value, but which secondary phase that it's in equilibrium.
Okay, thank you, Lidia. You focus mainly in intrinsic defects. Would it be more sense to look at impurities?
You mean
For dope, if impurities would be easier, I don't know. Why just intrinsic defects?
Doping would be a second step. Like the intrinsic defects, the idea is really because, in principle, the range the extent to which we can dope a material with an extrinsic dopant, it's really defined or limited by the intrinsic defects. So we need to start to understand the intrinsic defects, and then the extrinsic would be a next step, because there is also all the problem of solubility if a given extrinsic defect can really provide the carriers that you are interested or not. So this would be a second step. Thanks.
Yeah, so I guess let's thank the speaker again.
Thank you.